Hello, I'm Craig. Let's talk about cars. So this week we're going to talk about HVAC, heating, ventilation, and air conditioning, and cooling systems in regards to hybrid vehicles. We'll start off with a review from engines and AC class, and we'll talk about some of the nuances and differences as they're applied to hybrid vehicles. So, as you know, cooling and heating systems in hybrid vehicles operate on the same principles as conventional vehicles, but have unique operating parameters. Let's take a look at these. So what's the purpose of the cooling system? As you can see here, the purpose is to bring the ice up to an optimum temperature as soon as possible and keep it there under all conditions. A lot of people think the cooling system is there just to keep the engine cold. Not true. Cold engine is less efficient. We'll talk about some other reasons why in a minute, but also the cooling system is designed to bring it up to optimal operating temperature as soon as possible and keep it there under all conditions. Modern vehicles do a fantastic job doing this, much sooner than driving an older vehicle. If you've driven an older vehicle, and I'm talking, even up to 80s and older, they take a while to warm up. Especially get really old carbureted, old vehicles take a while to warm up. So, chalk one to the fuel injection. We keep the ice temperature in a narrow range for a number of reasons, such as, and here's the reasons why, highest efficiency and lowest emissions at operating temperature, vehicle drivability is enhanced, cold engines wear out faster, and used to heat the passenger compartment. And that's really kind of a byproduct of the inefficiencies of the ice. So the ice on a great day, modern designed engine, you might get 40% of that energy to propulsion. The rest of it's going to go to friction and heat and out the exhaust. So they capitalized on this, on the inefficiency, by using that excess heat into another little heat exchanger in the cars, the heater core, and a fan to warm up the passenger compartment. And overheated engines reduce efficiency and may fail. Obviously, they also pollute, so a lot more emissions on a hot engine. Cold engines, hot engines pollute. Basically, they wear out. Drivability is garbage when it's cold or it's hot. It starts pinging and running bad. So the cooling system's purpose is to, again, not only keep the engine cool, but get it to operating temperature as quickly as possible and hold it there. So all automotive ICEs, internal combustion engines, use a liquid coolant that is circulated via a water pump, usually mechanical, but could be electric. Even on non-hybrid vehicles, you could have electric water pumps. Through the water jackets, through the heater core, after warm-up, open thermostat, it goes through the radiator. Otherwise, it bypasses the radiator. You remember back into the engines AC class, you probably learned about that water cycle. So again, as the engine warms up, the thermostat opens up and allows a coolant into the radiator, and then that helps exchange that heat from the engine to the atmosphere through that fan that gets turned on. So turns on fan for circulation if AC is on, or if it's overheating or ECT is increasing, basically getting hot. So some vehicles have one fan that operates in different speeds, is duty cycled. Some engines have two fans. One that's your normally operated fan, and then one's for the AC system. If it turns on, like max AC, it's going to kick on that fan because of the increased heat load into those heat exchange units. So make sure they're both working as properly as possible. So we're familiar with this process and these components, but we're going to go over them again. Thermostat. Again, that's a regulated device that's going to open up based on temperature. It's got a wax pellet, or it can be electronically activated via the computer. And that's going to allow that coolant to leave the engine and go through the radiator to be, again, cooled. That heat can exchange into the atmosphere. Pressure cap, this increases the pressure of the cooling system. And we, of course, increase pressure because as pressure increases, we can increase the boiling point, right? So make sure you have a good functioning working pressure cap, not leaking. And I really don't like those kinds with a quick release valve on it. I just never liked them. Use the OE pressure, don't go higher. Don't go lower. Keep everything as designed and working functionally. Coolant tank. These come in various different types, sizes. They can be either part of the radiator. They can be overflow tank. It can be a degas pressurized tank. But basically, it's somewhere for the coolant to expand and contract because the volume of the coolant is going to change with temperature. And the water pump. So it can be mechanical or electrical. We'll get more into that in a little bit. You're probably familiar with the mechanical water pumps. We're going to talk more about electrical water pumps. And then there's a coolant, different types, IAT, OAT, HOAT, etc. My recommendation is not to use quote-unquote universal coolant from the parts department. I like to use what's OE, original equipment, and what's designed for that engine. The people who design that coolant and that's very special chemical makeup of that coolant know the alloys of that engine. So why would you want to run a universal one that works for many, many vehicles? And you're talking, okay, twice as much to buy a good quality coolant most of the time. Of course, there's outliers with, like Jags and expensive European vehicles, but you get what you pay for. So I like to use OE coolant. And again, if it's twice as much, you're talking is going from 20 bucks a gallon, 15, 20 bucks a gallon to 30, 40 bucks a gallon for an OE. I mean, some of them could go up to 60, 70 bucks a gallon, but again, how often do you change that coolant? And the damage you can cause to that engine is going to be a lot more than 60 bucks. So stick with the OE and you'd be good. So what happens to this conventional system when our hybrid enters idle stop? Now, this is the question as it relates to hybrids. On the conventional engine with the ICE, if the engine were to stop, what happens to the water pump? Yeah, that's right. The water pump stops. Obviously, it's mechanical. So we had to overcome that, or I say we, they did. I just study it and work on it and teach it. But the vehicle has to have an electric water pump that can keep circulating coolant even when the ICE is stopped. Are there ways to speed up the warm-up process and keep the ICE at operating temperature more efficiently? Yep, and we're going to talk about that in just a little bit, so hold on to that one. And how do you heat up the passenger compartment in EV mode? So if you're driving around in a hybrid and it turns to EV or even electric vehicle, non-hybrid, how do you heat up the passenger compartment if you either don't have an engine to create heat in your coolant or its engine's turned off and it's not creating heat? So we'll cover that in a little bit too. Let's get started. So basically, again, back to the cold engines. Cold engines collect fuel on manifold and cylinder walls, requiring a richer air-fuel ratio. So Prius vehicles up to 03, and I use Prius because it's the most out there. In fact, when I started designing this class, I found a report on the DMV about look for hybrid vehicles. Most registered hybrid vehicles in the state of California, Prius far out any other. I mean, 3/4 of the cars out there were Prius at the time. Prius is Prius. Okay, it's like Deere. 1 or 10, it's Prius. So I focus heavily on that, and also a lot of other manufacturers use Toyota technology. So once you understand the physics and theory, how a Prius works, you can apply that to pretty much any hybrid or electric vehicle at this point. So back to the point at hand, Prius vehicles up to 03 used a hydrocarbon adsorber, not an absorber, an adsorber, to reduce startup emissions. And then after 03, the second gen, they utilize this coolant storage tank to bring engine temperature up quickly and supply heated coolant to the passenger compartment heater core. Obviously, I'm going to show you how, not just give you a definition. And the newer Priuses, when you get 2010 and newer, they actually circulate coolant right around the catalytic converter, and other vehicles can operate. Like Honda uses one called a fire system, where they actually open up the throttle body, kick on the EGR, bring a bunch of air in the engine and fuel to heat up the engine, but the RPM doesn't go up because it's got EGR. So it's kind of a fascinating system, but everyone has their own way of doing this. I'm going to talk about these because these older hybrids use a hard component system, which means there's extra parts to replace that can fail. So we'll talk about those. So up to 03, on the first gen Prius here, the hydrocarbon adsorber is in its catalytic converter to reduce emissions on startup, and here's how. So here's your three-way cat. As it comes in, I'm going to focus on this three-way cat right here. So you have this bypass valves closed, so exhaust doesn't go straight through the cat. It's going to come up through this hydrocarbon adsorber, where the hydrocarbons stick to the surface of this adsorber here. And it goes through these passages and then out the cat, out carrying its way. When the computer deems worthy and it's programmed, this bypass valve opens and allows it to go through the cat, flushing this hydrocarbon adsorber out as well, to kind of bring the hydrocarbons through this cat once it warms up, so it can do its catalyst. In 2004, Prius introduced a coolant storage tank, and the reason I bring this up is this storage tank can hold just under a gallon of coolant, about a liter of coolant or so, and it can be kept hot for up to 3 days. I'm talking operating temperature hot. It is a vacuum thermos tank, so this coolant circulating in here is hot enough that if you drain this valve, there's that valve right here, right there's that valve. If you open that up in that spigot, that's operating temperature hot. So a couple things you need to know about that. Basically, the system utilizes a pump. Right here you have this pump, and you have a valve and temp sensors and drain plug, and it's going to bring water or operating coolant, operating temperature coolant, into this thermos. And how it does it is it's going to actually fill up this thermos with hot coolant, and then it pulls the hot coolant out from this spout tube, much like a hot water tank in your house, this little downspout. So as hot rises, right? So all the hot water is up, the hottest water is up to the top, and that's going to come down right down this spout tube and back out to the valve. To and from, we'll talk about that in a second. That's how it fills it up as well. So it keeps the coolant on the bottom, the hotter on the top. This spout can break down just like a hot water tank at home, but pretty much uncommon. So here's that valve I was mentioning. Basically, the system uses this water valve that directs coolant flow between the tank, ice, and heater core. So it's kind of this intricate system where it can utilize that hot coolant on startup, but also replenish it when the engine's at operating temperature. And I'm going to show you a couple different modes. Basically, the operations are preheat, engine warm up, storage during driving, and storage during ignition off. But before I talk about these modes, I want to talk about this valve. What's cool about this valve and what we can learn are a couple things. One, this valve is a known failure part. You know, it's a common replaceable item. And typically what happens is not so much the motor or this gear breaking, this worm drive, this valve position sensor right here, this Hall effect sensor, that tells the computer the position of the valve, so it knows which way to power it and how far. Otherwise, it doesn't know how long to turn on this motor and in what direction. Agreed? So the hybrid control unit is going to have to receive a signal from the position sensor before it activates this valve. If it doesn't receive an adequate signal, it's not going to activate the valve, and it's going to set a diagnostic trouble code. This also is the same over to HVAC. When you talk about temperature blend door actuators and mode door actuators, they too have a valve position sensor on automatic controlled HVAC systems. So if you have, and this is a common fault I saw as a tech from back in my day, was that if you have a actuator, you know, temperature, blend, or mode that is faulty, you're going to want to access the pins, right, and check the motor. And you're going to notice that when you turn on hot or cold, there's no power being sent to that actuator. Just like this one, if this was faulty, you would notice there's no power being sent to it. A reasonable person would assume that means you need to check the source where the power comes from, and that's the control module. You'd get to that control module and you would notice no power coming out. And so what would be the next step? Probably replace it. That's what most techs did, but to no avail. Same problem. Bummer, that was expensive. Those things could be $500 plus, if not more. So that can be an expensive boo-boo. Here's what basically has to happen. That control device, either the HVAC control panel or the hybrid control unit, has to receive a position signal before it sends a power signal to control the actuator. So you have to start off with measuring the position voltage at the control module, make sure the control module is receiving that position sensor, and then you can check for power coming out. So keep that in mind with this valve, also with any vehicle with automatic AC. Pretty common failure part and commonly misdiagnosed. So back to our 4 heating modes of operation. We'll start off with preheat. So basically preheat is enabled prior to ice startup. The ECM turns on an electric water pump on the storage tank, sending hot, let me move my little slider down here, hold on. Sending hot coolant from the tank to the ice head assembly. So here's what basically is happening. This is when we're preheating this cylinder head. We got to get that cylinder head up to operating temperature as quickly as possible. So the computer is going to operate that valve. Here's that valve we were talking about a little bit ago. It's going to turn on that pump, and it's going to pump coolant through the storage tank, and it's going to go, remember the hot's up top, it's going to push the hot water out first as it fills its bottom up with cold coolant. It's going to push the hot coolant out. Remember, the engine's off. You just started it. It could be ready mode running or not. But hot coolant's going to come out through this valve, which is directed to the cylinder head. And right now the thermostat's closed, so it goes from the water pump back over to the coolant heat storage tank water pump, and it's going to keep recirculating this way until the engine gets to operating temperature on its own, using temp sensors on the engine and temp sensors on the storage tank. So that's how it preheats the cylinder head quickly, get the engine up to operating temperature as quickly as possible. So after the preheat cycle is completed, the ice is allowed to start to the next mode is entered, which is engine warm up. So now the engine's warming up, it's got that hot coolant in the head, everything this kind of goes back to semi-quasi normal. The valve turns, turning off the storage tank and water pump. So as the engine heats, it goes out, the thermostat, instead of bypassing, goes out to the radiator, and it goes to the water pump, and you see it's feeding both this water valve right here, the heater core, and then back to the engine through that water pump. So this is kind of the normal warm-up process.